My name is Emma Yu. I'm from University of Texas at Austin. I want to first thank the organizers for having me here. I've been having fun learning a lot over the weekend. So I work with Neil Evans, Sally Dawson-Robinson, Karen Willesee, and Neil Turner on this project. So first, I'll give a really quick review on our understanding of protoplanetary disks and star formation. And then I'll move on to our attempt to find the optically thin tracer for the disk midplane. Later on, I'll talk about our finding and our modeling approach. So first of all, this is my version of the star planet formation picture borrowed from actually Jeff's website. The pointer, okay. So single star formations start from the collapse of very, very dense core in molecular clouds. Because there's some sort of rotation at the very beginning, so materials can only fall along the rotation axis, but not perpendicular to it. So we end up with a rotating disk around the newly formed young star. This stage is very valid. After probably 100,000 years, we enter a relatively stable stage, what we call T-Tauri phase, around solar-type stars. So this stage lasts for a few million years for solar-type stars, and with a relatively mild accretion rate of 10 to the minus 8 solar mass per year. After this relatively stable stage, the disk enter a very rapid dissipation stage. Actually, the next speaker is going to talk more about that. So the disk will dissipate in around 100,000 years. If you're lucky, we'll live with a planetary system. We've actually seen those disks in many different wavelengths in many different situations. So the plot on the upper left side, this is the HST Hubble image of the scatter light of the disk surface. So what we're seeing here is the central stars fall somewhere around here. The light hit on the disk surface and scattered into our telescope. The problem is we're only seeing the disk surface. We can only tell properties from the very, very surface of the disk through this kind of image. Another really dominant way of seeing those disks, actually there has been a lot of progress made in the past 15 years, is by observing the infrared SEDs. So what we're seeing here is a function of energy, the luminosity, the energy as a function of the wavelengths. So we're seeing a really broad spectrum. This part is emitted by the inner part of the disk and the outer part of the disk. But the problem is we want the disk to be relatively warm in order to show up in this wavelength. So again, we're seeing the relatively warm surface and the inner part of the disk itself. So with the development of amazing interferometries, we're beginning to see molecular line emissions from those disks. So the most common line we're seeing is 12CO, just because CO is everywhere, and this emission is really strong. The problem is, again, the lines are optically thick, so we're only seeing the very surface of the disk. But in order to understand planet formation, we want to see inside onto the disk midplane, because that's where planet formations are actually happening. So we try to ask some really fundamental questions, like how massive the disk is that's available for planet formation. It turns out we don't know that very well. So first of all, our understanding is heavily biased toward our solar system. The zero-order magnitude approximation is to simply smear out the mass of our known planets. So we have Mercury, Venus, planets out here. We just smear it out over the orbits, and then we add up the volatiles that's lost during planet formation process. So we add up the oxygen, the hydrogen, stuff like that. Then we end up with a surface density distribution, which is the surface density as a function of distance to the central star. And this is our or lower limit, or like the basic picture of the solar nebula. But there's a problem with this picture, because we assume everything we see today was the case when it was first formed. So we assume 100% solar tension, which is obviously not the case. We also assume all planets are formed in situ, so they're formed where we see they are right now, which we now found that's not the case. Planets migrate all the time. Another way of seeing this is to observe disks around other stars. So traditionally, this has been done by observing dust emissions. Okay. The problem with this approach is we observe those disks in sub-millimeter, so that we're only most sensitive to dust grains of around the same size. We know dust grains grow up into pebbles, into boulders. Once they grow into larger bodies, they're less emissive in those wavelengths, so we're not able to see them anymore. So we're really only seeing a small fraction of this mass from this approach. Annoyingly, the result from the dust emission and solar minimum mass solar nebula agree with each other really, really well, but we know both of them are probably wrong. So we try to ask the question, what if we just measure the disk mass directly from the gas phase? As Brandon just mentioned, 99% of the disk mass is actually in the gas phase. So this has been done before once with HD, with deuterium, because that's a less abundant isotope of hydrogen. The problem with that is that was done with Herschel. Herschel is dead, it's gone, it does not exist anymore. And also this line requires relatively high excitation temperature, so it's sensitive not just to the amount of material out there, also to the temperature of the disk. However, this example told us it's important to measure the disk mass from the gas phase because the mass they found was actually heavier than what people typically find from dust emission. And it's also way massive than minimum mass solar nebula. So our goal is to find the rare, isotopically rare molecule in order to allow us to trace directly to the disk plane and allow us to measure the disk mass from the gas phase. So we want to use this awesome array ALMA down in Chile, so that we can have enough sensitivity to probe very, very weak emissions. It turns out that's a really hard thing to do just in order to build a model, right? Just because the temperature, the density, chemistry, and radiation transfer, they're all coupled together. So we break the model down into 3 components. So ask me about the details later, but right now I'm just gonna focus on the big components. So we model the thermodynamical evolution of the disk by putting in MRI. Again, the next speaker is gonna talk more about that. And then we calculate the evolution of density and temperature in each individual grade point, and then run chemical model on the top of it. So we care about rare isotope locks, so we need to consider, say, UV desorptions and self-shielding and photochemical reactions, stuff like that. So we did that, and then we end up with a profile of chemical abundance, temperature and density for every single point in the disk for 3 million years. And then we run radiation transfer model on the top of it and try to estimate the optimal depths of those molecules. So this is the temperature profile. The takeaway, let's see. So imagine a torus of the disk. Here is the central star. And now we're taking a cross-section of the disk. So the x-axis is the distance from the central star. So the star is here, and this is the thickness and the height. So the disk surface is heated by the central star, and the heat propagates down. So that's why it's hotter here, right? It means hot. Sorry, this is the temperature in Kelvin. And the takeaway here is accretion heating doesn't matter that much if you're disk smaller. That's actually different from what people have been assuming. And takeaway from chemistry is in our disk model, we actually don't see CO phase out because the heating from the central star is pretty efficient, but we do see a drop of CO abundance due to the formation of organics. So carbon dioxide is primarily in the ice form that's inherited from the cloud, but CO is gone. So red means a lot, blue means almost nothing, and this is the abundance normalized by the amount of total proton number density. So we're seeing a lot of complicated organic molecules. Exactly what kind of organic we're seeing depends on the model and the initial conditions, but we tested with input from observational data and also from modeling data. It seems that this result is pretty robust. Okay, so last year, 2 years ago, there was a big discussion, discovery result of imaging CO ice line in a polar planetary disk. That's really cool because we can use that as a direct temperature tracer. Again, we probably don't have time to talk about it. So we're only trying to say if we don't see CO around, it doesn't necessarily mean that CO is phased out onto the green surface. There can be something else. Yeah. So after doing all this, we sit down and estimate the optical depths of different CO isotope blocks. And here we're seeing the optical depth in vertical direction for face-on geometry. So you're seeing a disk facing right in front of you as a function of the distance from the central star. And it turns out that C17O, the blue line here, is awfully thin beyond probably 10-ish AU, and C18O is awfully thin beyond 17 AU, I believe. So we hope to use that line in order to measure the disk mass with ALMA. So we proposed for a cycle 3 times. We'll see how that goes. So the idea is this will be the line profile. This is the velocity just because the disk is rotating. So say if this part is moving toward you, the inner part of the disk rotates faster, so that goes to the line shoulder, and then the outer part rotates a little bit slower, so that goes inward. So we have a double peak signature for a disk. And we can translate the luminosity, the intensity of those lines, and back to the mountain material that's giving up the emission. So that's sort of the goal. I'll leave the conclusion here and take questions. Thank you.
So that was really cool. I'm wondering if the result that CO can turn into complex organics in the disk is a new result, and if so, what does that imply? Is it possible to directly look at organics with ALMA also, or what's the future for that?
Yeah, so the problem is it will be really hard for us to see them. The way it happens is we actually see the growth of carbon chain in the gas phase, and then it's easier for those organics to phase out onto the green surface, so they will phase out onto the grains and just get out of the gas phase reaction network. But one encouraging news is people are seeing the depletion of carbon in the gas phase, I think as well as oxygen. So they're thinking about, okay, carbon might go to somewhere else, and it could well be the organics on the green surface. So it's encouraging that people are seeing it observationally already. Yeah.
Questions, anybody? I have one. So what are the prospects for imaging rare isotopologue snow lines with ALMA? Is it going to be?
Yeah, actually, I think this is unpublished result, but people are seeing it already. I saw a poster from Tybergen's group. They have C18O data on T-lip hydrate, so they are seeing Iceland at 30 AU, exactly where that's CFA group are seeing in N2H+, and they're also imaging N2D+. For some reason, I haven't quite understand yet.